connection to Science Night. Please stand by.
Welcome back to a very special edition of the Science Night podcast. It is our annual Festival of Fusion, where we look through all of the fusion energy news that happened over the past year, and we tell you about it. And, you know, I am basically an expert in fusion myself this time.
Definitely.
I solved it the other day. Let me tell you, what I did is I took standard Philadelphia cheesesteak.
Oh, no.
I put some chili crisp on it and fusion right there. That's basically it, right?
Sounds magical.
So the two actual fusion scientists are not very excited about my find, and maybe I don't really understand about how tokamaks work. So why don't I tell you who we got tonight? Of course, we got Dr. Steffi Diem.
Hey.
And straight out of Princeton University, Dr. Arturo Dominguez.
Hey, James, how's it going?
I don't know why I swallowed that syllable. It was going to go badly. I'm going to leave it in now just for fun. So I did my fun intro. I did a stupid joke about fusion. And now I know enough about fusion to know I know nothing about fusion. And I'm going to give it to the adults. And I'm just going to be here to do some fun jokes and stuff. So, Dr. Diem, take it away.
I mean, you knew what a tokamak was. There you go.
If I didn't know what a tokamak was by this point.
You knew the word.
Yeah.
Yeah.
I'm just thinking about the cheesesteak in your stomach doing fission as opposed to fusion.
Right?
You know, there was a lot of energy release at some point.
I mean, this is a good segue into Arturo. Tell us what is fusion?
Yes. So it's definitely not what James was talking about. Fusion is what happens in the inside of all the stars. It's when you have small nuclei, the center of the atoms, combining together to form bigger nuclei and releasing energy. Right. And that's what happens all throughout the universe. That's what happened at the very beginning of the universe. Everything, there was fusion all around. It happens in all the stars. And what we've been trying to do as a community, fusion community, for the last 60, 70 years is trying to reproduce that on Earth, where we can harness that energy and create electricity out of it. And it's been an exciting couple of years for fusion.
And it has amazing potential, too. If you're going to look at the amount of fuel you need for fusion to power your entire lifetime, this is your electronics, cars, your house, you just need the deuterium from 1.5 bathtubs full of water, and then the lithium from 5 laptop batteries. And then it's no greenhouse gases. The byproduct is helium. That's compared to the same amount of energy you have to get from burning coal, and you have to burn 280 tons of coal, which gives off 380 tons of pollution.
Exactly. It has so many advantages. The fuel itself, as Steffi said, is so abundant that you can have it for hundreds of thousands of years. We just haven't gotten to the point of creating electricity out of it. But I think this year has been exciting in the path to getting there.
And before we jump into the news, can you tell us how we can create these conditions in the lab?
Right. So we're talking about what happens in the inside of the sun, right? Why is it so hard for these reactions to happen? If you think about the reaction that I just described, you have two nuclei, which are both positive. And so two positive charges repel. The positives repel each other. The reactions don't want to happen. What we do is we've got to heat it up and put a lot of pressure in the system so that the nuclei do fuse together and we can get enough reactions to harness the energy. So there are two main approaches, and then combinations of the approaches or offshoots of it. One is the magnetic route. So when I'm talking about this fuel that's super hot, at that point, it's at the fourth state of matter, which is plasmas, right? So you have solid, liquid, gas, and then if you heat up a gas, you get a plasma. And so the sun is made out of plasma, fire has plasma, fluorescent light bulbs have plasma. And one interesting fact about plasmas is that you can control them using magnetic fields, using magnets. And we see this at night, actually. I've never physically seen them, but if you go really far north or really far south, you can see the auroras. the aurora borealis in the north and the aurora australis in the south, with these light shows, which are plasma that have come from the sun, and they've been guided by the magnetic fields towards the North Pole and the South Pole. So we can see there the effects of magnetic fields on plasmas. What we do in what we call magnetic confinement fusion is we build these devices that typically look like a donut or some variation of a donut.
Cord out apple.
Or a cord apple, right? Some torus that you have the plasma, very, very, very hot plasma in like the jelly of the donut, right? And then your machine is a metal torus that surrounds your plasma. So if you think about it, the idea is to keep the hot plasma away from the cold walls. That's the basic of magnetic confinement. We put the plasma, we heat it up, and this happens at orders of seconds. That's the time scale of this. What about if we do another approach? If you get all of the fuel inside a little tiny pellet, and then you bombard the pellet from all sides with some form of energy, and then you compress it so you reach these very high pressure, high temperature conditions, and then make fusion happen there and then just let it explode. What I just described is the other main method for fusion, which is inertial confinement fusion. And it's inertial because it all happens by the inertia of the compression of the pellets.
I think you also just described grad school too. Just kind of like bombarding with pressure and letting it explode.
So much pressure.
Except that these happen in picoseconds and not in way too many years. Right. But you're right. So it is a lot of pressure at an instant. And these are amazing. The compressions are of the order of 30 times in radius. That means that these little pellets, that they're actually the size of peppercorns, analogously to compressing a basketball to the size of a pea.
It's wild.
It's wild, right? And to make that compression happen symmetrically, it's just insane. But they've done it. And as we'll talk about a little bit later, they did it really well this year.
Yeah.
So that's inertial confinement fusion. And then there's stuff in between. There are methods in which they use some of the characteristics of inertial confinement with some of the qualities of magnetic fields to create some advanced confinement schemes. And so there's a lot of different hybrid approaches to fusion, but mainly those are the two broad approaches. There's been some exciting news in both of them in this last year.
I'm excited.
Should we jump into the news, the highlights of 2022?
I do have to point out, I saw a big difference between the two of you. You're telling me so much about yourselves just by one person referring to a tokamak as a donut, the other as a cord apple. Without knowing anything else, we know which person is putting Instagram pictures of them like running for fun.
Which has a cord out apple in their basement that's being built. That's me.
Who has to stop consuming donuts? That is me.
Well, before we go and jump into the news for 2022, I will throw it back to our episode last year where we ended it with a segment of what to look forward to in 2022. And that was the Joint European Torus, or JET, was in the middle of their first deuterium tritium campaign since 1997. And their results should be coming out shortly. That's how we ended it. The reason why that campaign was important, because a lot of our experiments are run with just one component of the fuel, deuterium. It's a heavier form of hydrogen. It's a way to study how well you can create these magnetic bottles to efficiently confine plasma, or the fuel for fusion, before you actually look at energy generation and bringing that into the picture. So with that context, we're going to jump into the beginning of 2022, which was JET's first deuterium tritium campaign results. Arturo, you want to talk about that?
I'd love to. As you pointed out, the deuterium tritium campaign has been, we've been waiting for results from them for many years, because only two machines in the world magnetic confinement machines have run deuterium tritium. One was JET, and the other one is actually here at where I work at the Princeton Plasma Physics Lab, the TFTR torus. And this was, in the 80s. So it's been a while since our community have been looking forward to these results, and they got to some exciting powers. So, and I'll let you, Steffi, take it away with the actual numbers for this.
Yeah. So they were able to produce 49 megajoules of fusion power. This was, to put it in context, tripling the previous record that they made. And it demonstrated that in a sustained, so for a longer time of actually running the experiment. That was the one thing that was really important. Record levels of fusion power. The other thing that was really important was they did this experiment and achieved these results using fusion power plant like metal walls. Because the first time they were doing experiments with metal walls, it wasn't efficient. They weren't getting the predicted results of their experiment. They're actually getting low confinement results. And so they went back, looked at how can you refine your experimental campaigns and how you run the experiment to get that better predicted results. And they did it. And that really gave us confidence that fusion will work on our planet. And it's a great example of what you can accomplish through this combination I mentioned of improved physics understanding and how you advance, how you run your experimental designs. And other thing that we do oftentimes is we have measurement devices that kind of give us keys of what's happening. And we take that information and understand what deep down what the physics is happening, and you can refine what you're doing. So I was really excited to start out 2022 with that.
Not only did they get to these 59 megajoules, they sustained it for 5 seconds. I mean, that was just the amount of time. But then when you look at one of the things that we as fusion scientists are interested in, this value Q, which is the amount of energy that went into the system versus the amount of energy that went out, right? If you get to 1, that's what we call break even, that the same amount went in and out. It wasn't quite as high as we want for Q, right? It was like 0.33, about a third of the energy that came in as the amount that went out. So it was very exciting in the science and engineering, but still not quite getting to that milestone that we wanted to get to.
As an anatomist, I use megajoules all the time, so I know exactly what you're talking about when you say like 59 megajoules. But for like people who maybe don't use that measurement, what are we talking about with 59 megajoules of power? Are we boiling water, or are we lighting the Lincoln Financial Field for one NFC championship game?
A Big Mac has 563 calories. That is 2.3 megajoules.
Oh.
Okay. Yeah. So we're at like the 25 Big Mac range.
Okay.
Right. I love that.
Look at us. Pushing the limit.
Okay. This is a way different Big Mac index, right?
Yeah.
Can we petition U.S. Fusion Energy to only report their findings in Big Macs? Mega Big Macs if it gets to like a really big number. Maybe like a kilo Big Mac.
Right. So when we make a small advancement, it's like adding fries to it, maybe.
Oh, yeah. See?
We got a Big Mac with fries.
Oh.
This is why we do science communication, people.
Does that mean we have a sponsor now? Like a corporate sponsor?
They're looking for anything to change their image. I'm sure they get it on that.
I'm fusing it.
One of the things that you really pointed out that I've been hearing a lot since I've been hearing you talk about how bad sometimes reporting is on fusion breakthroughs and stuff like that is you talked about how you have all of this stuff in the jet experiment that will, by like it being there, make the actual reaction less efficient, right? So we have all this stuff in the experiment, and that's like different than if we're looking at like a fusion power plant, right? Where we're looking at how to make the actual reaction more efficient rather than to learn something about the physics or the reaction and that kind of stuff.
Yep. Up until this point, and everything that we have right now is a science experiment, not optimized to create, generate, and deliver electricity. It's really, like you said, giving us that deep insight that we can use to test our models, to build bigger devices.
Yeah, and I would take it a step further, even with and we'll talk a little bit more about some of the excellent scientific results we had this year. Even with this, we are still far away from electricity in the grid. There's still a lot of technical challenges there. Not to undersell the the milestones that did happen this year, there's a lot of challenges, both in physics and engineering, that need to be solved.
But exciting is still exciting, right? Excitement for excitement's sake. Take a
Yeah,
lap.
and we'll talk a little bit about what challenges are left. But yeah, this is the physicists in us have been giddy this year.
Yep.
Let's jet our way to, what is this obscure town, this obscure building? White House?
Yeah.
Maybe you know something about stuff. I don't know.
Yeah, I mean, we talked about last year, we all came together as a community to come up with a plan for commercializing fusion energy. And then we delivered this plan with like this big webinar and everyone was excited. And then nothing happened. And then February 2022, I got an email inviting me to the White House. So I'm like, something is happening.
I got an email inviting me to a Zoom meeting.
Yeah, I saw you on the screen. And that was amazing.
I must have had my spam filter all weird because I didn't see the thing. But maybe podcasting will be part of phase 2.
There you go. Yeah, so it was the White House Fusion Summit, happened in March 2022. We did have an episode where I talked about it in Science Night, but we're just gonna kind of highlight in this news, the fusion news for 2022 now. It was a White House summit, and it was on developing a bold decadal vision for commercial fusion energy. This was building on both our community plan and the advancement in technology that actually allows us to finally build these power plants. Specifically, in this case, it was all leading towards building a fusion pilot plant in a decade.
That's fast.
Yeah.
It's actually a very aggressive timeline. But a lot of the emphasis was we've been developing this fusion ecosystem with more and more private companies really pushing to move the timeline up with innovative technologies and approaches. That was a lot of the emphasis of like, can we leverage this and leverage the universities and the national labs and the private companies and our international collaborators to really push this forward and try to have fusion make an impact in climate change. This is really it, right? That we want to be relevant to the global warming conversation. If we're saying that fusion is going to be in 50 years, then that can't be.
Well, and it was also giving a challenge to fusion too, that this is the time that we can actually support a just and equitable energy transition to benefit all stakeholders, to be inclusive, to not disproportionately cause harm to communities.
Opposed to how energy sources all throughout in the past have done it.
Yep.
This is a new approach in which we've got the opportunity as a new energy source to do it right.
So what happens when you don't put equity and inclusion at the very beginning of your efforts to do like a nationwide rollout? What are some of the examples that we can point to of like, yeah, this is why we're doing this now?
The United States of America.
No, not the U.S.
Right? By redlining, you have communities that are suffering from the impacts of climate change, mostly communities of color.
So in addition to that, a lot of the waste, a lot of the burden from the energy production has been disproportionately burdening communities of color and other disadvantaged communities. So number one, the benefits of new energy sources have not been equitably distributed. And the burdens have been also disproportionately going to communities of color. Additionally, if we're not working with the community and we're not seeing fusion as more than just a technological challenge, but the societal impact that fusion can make, and we're working with the communities that are going to be where the plants are going to be built or where the extraction is going to happen, then we can't expect to have the buy-in from the communities once we're at the commercialization phase. Then they will look at the fusion ecosystem as, these people that have not been in the conversation that are just trying to impose things on us, right? And then you get NIMBYism, not in my backyard. Mm-hmm. You get, community groups against what you're doing. You get local governments against what you're doing. This is moving beyond the research and development phase to the point that we really have to take into account where we're going to put these plants and make sure that we do this right and that we do get the buy-in from communities.
More than that, too, it's understanding their concerns and incorporating their thoughts and opinions during the process too.
The fact that that conversation is happening and is like part of the White House summit and is like at the very foundations of like, hey, we should do fusion energy as an actual source of energy in the United States and like talk to people about it is almost more exciting to me than the fact that we can prove that fusion can work.
Yeah. I remember several times, like a few of us in the community or the infusion community have sat around and be like, I can't believe we're having these conversations now.
Good work. I don't have a good transition for that. Good job.
There's a couple other things that came out of the White House Fusion Summit too. I mentioned this charge, on the scientific and doing it in an equitable way. But there was also this announcement of a fusion coordinator, a fusion lead, which allows us to work outside of our box within the Department of Energy. We can do cross-departmental work now, which kind of allows you more flexibility in how you fund things and get things done.
Like a central node of leadership. That's really important.
I like that we have at the same time like talks of equity and inclusion and then also talks of a bold and aggressive timeline, because so often as a point of, oh, why would we talk to people and include people? It is because, stuff like that just stops progress and slows things down. And here we have like direct evidence that we can be bold and also make sure that 15, 20, 30 years after we figure out how to do all this, we don't have a bunch of people in like some kind of sacrificial zone where things have gone really poorly.
Well, extend it beyond that. It's generational, the impacts too.
Not to say that these meetings are a kumbaya moment for us. I mean, there are pressures, right, from industry to move fast and from investors. But one of the things that we push in these conversations is that it would be a shame if we developed the technology, but then would not be able to deploy it, right?
Yeah.
There are examples. There are advanced fission reactors that would be very beneficial, especially in the fight for climate change, but that we can't deploy because we don't have community buy-in, and we don't want that to happen to fusion.
That's a great point. Also, you got Hershey Kisses, right? Or M&Ms. What did they give you?
Oh yeah, I got presidential Hershey Kisses. They didn't send you some via Zoom, Arturo?
No. So just for context, Dr. Diem was there in the White House, super fancy. And I was up in a screen in a Zoom call, just looking down at everybody.
In New Jersey.
Yeah. And they got fancy dinners and apparently Hershey Kisses.
Yes.
He's a Scranton guy, that President Biden. This guy got to have Pennsylvania representing there.
Yep. Should we move from the White House to one of the other major events of the year?
Let's do it.
Okay. That was the National Ignition Facility reached ignition in December 2022.
Yeah. Amazing if true is something I read 1,000 times on the internet.
Right?
Yes. Exactly. So definitely the highest profile piece of news, which, you probably have already heard about, is that in this approach of inertial confinement, right? The one with the pellets being shot at by lasers. With that approach, at the biggest facility in the world, the National Ignition Facility, which is located at Lawrence Livermore National Lab in California, on December 5th of last year, right at the end of the year, they were able to have not only break even, not only did they pass that Q equals 1, they had ignition. They got to a point in which heat from the reaction was fueling the reaction to keep on going. Kind of like you don't have to keep on throwing matches into a fire for the fire to burn. The fire will burn itself, right? Because of the heat that it's itself generating. This is what happened at NIF. So they launched approximately 2 megajoules of laser power.
So what is that, like one Big Mac?
It's about of the order of a Big Mac. Of a Big Mac.
Okay, so one Big Mac worth of energy.
Now I'm going to think of energy. Sorry. Now I'm going to think of the Big Mac energy from the lasers. They sent about 2 megajoules of energy in these lasers. It hit this little gold cylinder, which houses the pellet full of fuel, and turns that laser energy into X-rays, all of which hit the pellet of fuel, compressed it, and generated about 3 megajoules of fusion energy, right? So 2 megajoules of laser energy turned into 3 megajoules of fusion energy out.
Mhm.
So 1.5 times out.
Half a free Big Mac out of this
Right,
reaction.
there you go.
Out
There
of,
you go.
yeah.
Out of nothing.
This was a huge milestone for the fusion community, and really one of the major milestones that we have been looking for in the search for fusion energy. It's can we get to a point that we get more energy out than in these reactions? And we have proven experimentally that we can actually do it.
I was super excited to watch this press release because we can't just have a press release. We got to build up to it and have this big thing. So the information was out there days before the actual U.S.
Yep.
Fusion Department of Energy press release. But the simulcast did not disappoint when you have the person from Lawrence Livermore doing like the picosecond by picosecond breakdown of what was happening, like we're watching an M. Night Shyamalan movie or something. It was great.
I think the fact that everybody knew about it a couple of days in advance just goes to show how excited all of the scientists
Yes.
were when this happened. And I imagine being in that room, I would have been one of the first people to just like yell it outside. It's like, we got to break it.
Well,
Yeah, I would not have been able to keep my mouth closed. It was funny because one of the questions in the press release was, if this happened a week ago, why are you just now telling us this? And us scientists were like, are you kidding me? Like, you've got to do your due diligence. Like, they can't just get some initial figure in your screen and say, we got it, call the press.
Yeah.
Like, this has to be, they were sending it. And the poor scientists that weren't involved in that shot had to go and review the data. They effectively did a mini peer review before they released it, right?
Yeah.
All compressed to a week.
It's a lot of work. It's a lot of work.
I can tell you where they didn't spend their time is like their graphics package or their background. I'll tell you that for free. They can they really need to get a Canva Pro subscription or something like that.
You can tell that they do not give us money. We are, right?
When the Science Night podcast has a better graphics package than a Department of Energy major press release.
What does it say that I'm used to bad graphics? That when I saw their graphics, I was like, "Ooh, nice graphics."
Me too.
They used a serif font. Ooh, fancy.
We're so bad.
Like, that looked amazing. I'm usually like hand drawing my own stuff.
Yep.
Okay, so we did the big amazing thing, created more energy out than we put in. Still remaining challenges. Still a lot left to do.
I would say that it was very telling, when the news came out, it went kind of by waves, right? There was like wow, this is amazing. But then very quickly, a lot of people were like, okay, hold on, but what does this say about fusion, about energy in the grid? Are they hyping this? There were a lot of debate of like, is this hyped? Are they being transparent? All these things. So I feel that they were responsible in the way that they shared the information, that they weren't saying this means that electricity is in the grid tomorrow. But I would highlight, for physicists, this was an amazing moment because it did show that you can get more energy out than in. But even when you're looking at it, when you look at how much energy went into, like, was required to run the lasers, those lasers were super inefficient. They're like 1% efficient. I think they required like 400 megajoules, so like 200 Big Macs, to run the laser for that shot, and just 1% went into the laser energy. It's not that this isn't the latest technology. There are more advanced technologies than lasers and all of this, but it just goes to show that for the grand challenge of producing electricity going to the grid, this is just one step, right? We need to be able to turn these energetic neutrons into electrons in the grid, into electricity. And there's a bunch of technological challenges that are left there that are being explored all throughout the world, but that still need to be resolved.
And we can break it down into kind of like 3 buckets: science and tech things, challenges that we need to overcome. And it's sustaining the conditions for fusion. So this is having it be at the power plant like cycle and making sure it's happening long enough and repetitions high enough in the case of inertial. The second is developing materials that can withstand these extreme fusion environment. And the third one goes to developing the technology to breed the fusion fuel and generate electricity. But when we talk about developing materials that stand these extreme fusion environments, we're talking temperatures 10 times hotter than the sun. And then we're talking that they're having to deal with energetic neutrons. It's a neutral particle that's one of the products. It's going really, really fast, and it's hitting things, it's bumping atoms, it's moving things around, and you need to have material that can withstand all of that bombardment.
We've never even been able to test it, right? We don't have a facility that creates the energetic neutrons that we need at the right amount of fluency, like the right volume of neutrons that you could put in a little piece of metal and say, how is this going to react? We aren't even capable right now of doing those experiments. So we rely a lot on simulations and on experiments with lower energy neutrons, but it's still a lot. There's a lot of technological advances that need to be solved.
Now that we've kind of like solved the physics problem of we can do this on Earth, does that help in some of these like more engineering type questions of refining materials, creating more efficient things, or is it still kind of the same timeline we're talking about going forward?
Right. I would say in and of itself, the fact that we got ignition doesn't help us solve those technological issues. It does give momentum to the field to say we're going in the right direction. Let's, and it gets some visibility to the field so that more people get excited and want to join this effort, and maybe, support, both public and private support of it might go up. But these are still technological challenges that are being tackled. I think the main thing and the most exciting part has to do with the private companies that are joining these efforts and trying from their own side to help solve a lot of these challenges, in addition to universities and to national labs and labs all around the world we're all sort of focused on solving all of these challenges in parallel.
And I think that leads us to our last point that we're going to talk about. So what DOE launched last year, one of the things was a milestone funding opportunity announcement. This is similar to what was done in the space sector that allowed commercialization or private companies to get into this, space sector. And so now we're having that was launched for fusion.
So what you're telling me is we got some good PR and we're going to harness that and turn it into dollars. We're going to turn subatomic particles into money now, which then that'd be turned into science.
Yeah, it is effectively the Department of Energy saying, yeah, we believe that this is the way forward and we're going to help fund these efforts. But you have to give us milestones. That's why it's called the milestone program. Give us some milestones that you believe you can reach within the next few years, so that you make a credible case that you can build a fusion pilot plant, a first of its kind electricity producing fusion plant out of the support that the public is giving you and that you're getting from private investors. The metrics for the milestones were technical metrics, but also business metrics, right? Do they have a credible business case to make? Do you have a credible plan forward? As Steffi was pointing out, something that we were particularly excited about was that one of the metrics for these proposals was, do you think through what is the social benefit that your proposal can give, and make sure that you are taking into account the energy justice arguments for where is the technology that you're developing going to be deployed? Are you taking into account the voices of communities? Are you creating climates within your companies that lead to a diverse and equitable workforce? All of these arguments that we've been discussing earlier and that they were signaling in this White House event are there in the proposal. So we were particularly excited about that.
And this is the first time I've seen it in a proposal as part of the criteria that you were assessed on, which was amazing. So should we do any predictions for next year?
I know, since we're really good at it, obviously.
It was a little bit easier last year because Jet was just running the DT campaign.
Do you want to talk about the thing you're going to in Paris at all, or wherever the place in Europe?
I'm leaving tomorrow for France. I'm going to a technical meeting for IEA on decommissioning of fusion facilities.
Pardon? Mon Dieu?
Yeah. Because, you know, that's what you have to do. When you're starting to design, you have to be thinking about the whole entire life cycle. And I get to see ITER. I am so excited because I've never
You're
seen
gonna
ITER
ITER?
before. Yes.
So let's be good science communicators and define ITER.
Okay, ITER is an international experiment that is the first magnetic confinement experiment that was actually designed with the intention of producing more energy than you put in, so reaching a Q greater than 1. It is a very large international experiment, and it has been delayed. So, while it may be the first one that was built and designed to achieve that, there's another one in the U.S. called Spark by a private company, Commonwealth Fusion Systems, which has a faster timeline. So I guess we have a lot to look forward to the next couple of years.
So you're going over there to like whip them into shape, or
Just hang out.
When you look at ITER and like the facility that they're building, it's amazing.
You've been there before?
No, of course not. I want to go. That's why I'm so jealous.
oh no, am I creating a rivalry?
Oh, 100%.
It's like I'm used to like magnetic confinement devices being like, I don't know, 15 feet tall. This one's like 11 stories tall, the building.
Wow. Okay.
Yeah.
Going there. Have fun finding somebody for your next year end of year review, because I'm not coming back.
I mean, maybe we'll just have to find like senior scientists over at ITER, right? Like,
is that the only prediction we have? Arturo is predicting he will not come back because he's not going to ITER.
Yeah,
Arturo is taking his ball and going home. It is a prediction.
maybe you can take one of the many tennis balls that Dartmouth students throw at Princeton students when they play hockey against each other. Anywho, maybe we get Joe from Scranton next year. Steffi's got connections, right? He can bring us all Hershey Kisses.
Sure. Yeah. No, I think we're going to see a lot ramping up. We're going to see an announcement from DOE on the companies chosen through the milestone program. So they're going to start ramping up their design teams, the Fusion Pilot Plant.
I'm actually particularly excited about how they're going to implement these community plans. I really want to see how us scientists start engaging with communities and like how we can get their feedback on the process. I think it'll be exciting. I don't know what we're going to learn. That's the whole point, right? So I think this is particularly exciting.
So my prediction is carne asada cheesesteak. Like, that is the fusion that we really need going forward.
Carne asada cheesesteak.
I want
do carne asada with like a queso instead of a whiz. Although maybe we do whiz. Keep a little bit of that Philly in there.
Pepper jack or pepper.
Ooh,
that sounds delicious.
Yes, and
that sounds pretty good.
I think so.
Yeah.
I think we did it. Hey guys, we nailed it. We'll see what happens next year. I got big hopes and dreams on this new cheesesteak situation, but whatever happens, you will hear about it here on the Science Night podcast. Arturo, we gotta have you come in for like more of these more often. We got you a good mic now. We might as well have you come on and talk about other science things for fun.
I would love it, please. As long as you take me to ITER.
Yeah. Well, if Arturo is on here, we're going to talk about it all on our social media profiles. If you want to follow me, I am at James_Reed3 on Twitter. Steffi, where can everybody find and follow you?
You can find me on Twitter at Steffi Diem and Instagram at Starshippin'.
And Arturo, other than not at ITER, where can everybody find you?
On Twitter, I'm at ArtDomi, ARTDOMI. Or at home at...
And your social security number is?
My social security number?
Yeah. Well, you can follow the podcast at SciNightPod, and you can visit our home on the web, SciNight.com, for links to all our past episodes, the people that we talk to, the things we talk about, and, of course, our merch. You can find it all at SciNight.com. We're going to be back when we get back with a new episode. I'm not sure when this is dropping, but just check social media that we talked all about. Hey, why do I gotta tell you all this stuff at the end of, just listen, refresh the feed, subscribe, like, ring the bell, and then when we have new stuff, it's gonna come out. This is special. I'm just gonna walk away.